which is also by which it is also called the boundary layer thickness, the definition needs to be modified. So two new concepts I am going to introduce in this class, and we'll see how those concepts can provide you with a sufficiently accurate definition of the region in which the effect of viscosity remains important. That's what we would like to know. So the next step is something which is called as displacement thickness. So what is displacement thickness? We understand that near the solid wall, the velocity is smaller than the free stream velocity. So of course, in viscous flow, there would be a change, a reduction in mass flow rate inside the boundary layer. Had the flow inside the boundary layer, had it been inviscid, then the velocity would be simply equal to u infinity. And now it's not u infinity, it's rather vx, which is smaller than u infinity. And only at the edge of the boundary layer it becomes equal or very close to the free stream velocity. So there must be some reduction in mass flow rate in the viscous flow inside the boundary layer. So let's try to quantify that. And the reduction would simply be the difference in velocity multiplied by rho integrated over the entire thickness of the boundary layer. I am assuming that the depth is taken to be unity. That means in the z direction, it's not affecting the velocity. So if I have to evaluate what is the reduction in mass flow rate, I simply multiply the delta u, what it should be in inviscid flow, what it is in viscous flow, the difference multiplied by rho into area would give me the reduction in mass flow rate due to the viscous nature of the flow inside the boundary layer. Any question? Okay. So if you'd like to equate this situation with the inviscid flow, so what we need to do is we need to raise the platform, what you have seen in the previous figure, raise the solid platform, let's say by a distance, by an yet to be evaluated, yet unknown distance delta star. So some amount of flow area in inviscid flow you are completely obstructing in order to obtain the same amount of reduction in mass flow rate. So previously, whatever be that value, you are making sure that delta star distance will be blocked for flow so as to make the reduction in mass flow rate equal to the reduction in mass flow rate which you would obtain because of the viscous flow. So if you have blocked out this delta star, then what is the mass that you are not allowing to pass? It must be equal to u infinity, because in inviscid flow the velocity would be u infinity, and of course rho would be there. So for per unit depth, the reduction in actual mass flow rate is equated to a hypothetical situation of inviscid flow with a reduction in area. And when both these two are equal, the distance by which the platform is to be raised, which is delta star, is known as the displacement thickness. So I can, and for incompressible fluid, and u infinity of course is not a function of y. So I can have this from 0 to infinity can be approximated by 0 to delta, because nothing happens beyond delta, or whatever be its effect, it's going to be extremely small. So delta star, the displacement thickness, can simply be evaluated by this. Any question? Okay, so what is the advantage of defining something like delta star? What advantage would I get which would reduce the experimental problem or experimental uncertainty in pinpointing the edge of the boundary layer? Is a Can I have some comments from you? Why do you think delta star is a better choice than the delta displacement thickness or the boundary layer thickness, which we have defined in the previous slides? Anyone with some any idea? Look at this integral. If you examine this integral, uh, what is going to be the value of this integrand as you approach the boundary layer, edge of the boundary layer? So you have the solid plate and you have the boundary layer where you have Vx. Outside of this, you have U. So what would be if I approximate this integral as a sum of infinite steps? What would be the contribution of 1 minus u by u infinity as we approach towards the edge of this boundary layer? Is it going to be significant or insignificant? At least you answered that.
Insignificant.
Insignificant. So therefore you do not you this value is going to be small as I approach this, and we have discussed this. We have discussed that the error associated with delta comes when we approach this edge. So because you and I will probably place the edge in distinctly different locations. But in this case, it really does not matter, because whatever be the errors that we are introducing in this region will have a very small impact on the value of delta star. So as the integrand vanishes near the edge of the boundary layer, any experimental error which is reflected in U near this edge will have very small effect on the value of delta star. So delta star is going to be a much more stable indication of the phenomena inside the boundary layer as compared to delta. So that's why displacement thickness is preferred over just the thickness of the boundary layer. Questions? All right, and there's one more thickness which has been used in the literature of boundary layer. I will talk about that now, which is known as the momentum thickness. Since displacement thickness is reduction in mass flow rate, so of course the momentum thickness has to be the reduction in momentum flow. So what is the definition of momentum thickness? It is the reduction in momentum of the fluid that actually flows in the boundary layer. So whatever flows inside the boundary layer, the expression for that we have already obtained. Whatever flows inside the whatever we could obtain from here. So whatever flows inside the boundary layer, had there been no effect of viscosity, it would flow with a velocity u infinity. But since I have the viscosity, it is now flowing with a velocity equal to small u. So this u infinity minus u is the change in velocity of the mass which is actually flowing in it. So let's say that u infinity minus u term is not there in this expression. There are two dy's. There should be only one dy. We need to correct that. So rho u dy essentially gives me what integrated from 0 to infinity gives me the amount of mass flow rate which flows through the boundary layer when the effect of viscosity, we are considering the effect of viscosity. This is the real flow, the actual flow. This much of flow would have the momentum if we consider u infinity, but we do not have u infinity it is flowing with U. So the reduction in the momentum of the actual mass of fluid which is passing through this must be equal to this multiplied by the change in the velocity. Am I clear? Is there is there any comments that you may have up to this point? So this is what the reduction in momentum flow rate is. Now, in order to obtain the same reduction in momentum, let's say I have to raise the platform, the plate, up by a distance equal to theta. So if I reduce the flow area by raising the platform by a distance theta, then the reduction in momentum must be equal to rho u infinity theta star. That's the mass which is not passing, which is not allowed to flow now. And that mass, if it would have been passed to flow, it would have been allowed to flow, would have a momentum equal to this mass multiplied by u infinity. So theta star is the reduction in momentum flow rate, which is equal to whatever we have discussed over here. So if we equate these two, we get the expression for theta star as there is another u missing here. So u infinity missing here. Please change this. I will do that. So this is essentially then the definition of the momentum thickness. And once again, you can clearly see that the integrand vanishes near the free stream. So as the integrand vanishes near the free stream, any experimental error associated with the evaluation of U will have very small effect on the accuracy of theta star. So that's the reason the instead of boundary layer thickness as such, the momentum and displacement thickness, which are derived quantities, are sometimes used to express the effect of viscosity in the layers which are close to the solid surface. Do you have any question? Okay. We will keep these definitions in mind, and when we talk about momentum integral equation in the subsequent classes, you would see that the theta and delta star would appear in the expressions, and it's very straightforward. It's almost like this name sounds something like very serious, but momentum integral equation, once you learn how to use it, it's going to be simpler than the Navier-Stokes equation, which you have handled in your second year. What I'm going to do now is I'm going to give you some handwritten note that I have written. It's not there in your text, but I talked about the Blasius solution, which is some sort of an analytic solution. I will very quickly go through this. The important part is not the solution process. Okay, the important part is what are you going to make with the solution? Is there something, some additional information, insight which can be obtained about the process if we could solve it analytically, followed by numerical solution of the governing equation? So what I am going to do is I'm going to simply show you some of the steps, not all the steps that are not important. The concepts are there are key concepts I will mention, and you can just be with me for the next 10 minutes, and we will convert the governing PDE to an ODE. So we have two equations. The first equation is the equation of continuity, and the second equation is the equation of motion. And you look that the equation of the motion does not contain the del square Vx del x square for the reasons that we have already discussed. What Blasius saw by analyzing data and is that the velocity in the x direction, when plotted against a non-dimensional distance from the solid wall, there is a definite relation between the two. So the non-dimensional velocity and the non-dimensionalization factor for velocity is u or u infinity, and this is going to be related to the non-dimensional distance from the solid wall, and the non-dimensional distance is y, which is the dimensional distance is y, and the non-dimensionalizing factor is delta, which is the local value of the film thick of the boundary layer thickness. But we understand that this local value of film at boundary layer thickness could be or is a function of x. So this equation is to be solved with the boundary conditions that I have already discussed. So the first step is to define a stream function. You know what is a stream function, and you know the relation between Vx and Vy in terms of the stream function. So when you do that and substitute in this equation, then as psi is an exact differential, so the stream function is an exact differential. This part it should come back to you, and then this equation gets automatically satisfied. So introducing a stream function enables us to get rid of one equation. That means we have one less equation to solve, and then all the velocities are to be converted not as Vx or Vy, but in terms of the stream function, and then we can solve the equation number two in the way. So this is my equation, and we could see that near the boundary layer, near the boundary layer, the velocity is going to be approximately equal to u. Y will tend to delta, and del Vx by del y. That means the gradient or change in the velocity with respect to y would also approach zero. So when we consider these approximations, then we can an order of magnitude, an approximate analysis of the governing equation for the boundary layer. So what we do is we understand that near the edge of the boundary layer, this term will vanish, and this is going to have an order of this, whereas the right hand side will have the order of nu, where nu is the kinematic viscosity, and del square Vx by del y square would simply be equal to u by del square. The purpose of this analysis is to get a relation between x and delta. So how it is done? So if these are equal, then delta will be, it is not an equal sign. Delta will be of the order of nu x by u, where u is the free stream velocity. Now, if we go back to the previous one, we understand that we are defining a combination variable. One way to solve a PDE is to define a combination variable, and the combination variable here is eta, where we see that it explicitly contains y and implicitly contains x through delta. So if we could get an approximate relationship between delta and x, that should suffice to get me some expression for eta. And that's what we have done here. Eta is y by delta. And when I substitute this form of delta, of course, this is not equal. We would get this as my choice for the combination variable. So all the terms that we see over here, instead of del x, I have to express it in terms of eta. In terms y, del y is to be substituted by del eta, and so on. So we introduced a stream function. We invoked the method of combination of variables through which we have obtained this eta. And since this equation is dimensionless, I'm just simply writing a dimensionless stream function. And the hope is once I substitute this in here, I would get an ODE between F eta and eta. That's how you convert a PDE to an ODE. So I would just show you some of this. If you are interested, you can take a look at it. It's not in Fox and McDonald, but in earlier versions it was there, but it's there available in the net, so you can take a look at it. So I find out what is Vx, which from the definition I know it's del psi del y, which is the stream function. Then I convert everything in terms of eta. So what we get is this one, Vx is u df d eta. Similarly, I can find out what is the expression for Vy. So I get an expression for Vy. So these two are the main results which we are going to use subsequently. But let's proceed with this. It has been shown by Blasius is that, and you can take a look at the few more steps which are needed to ascertain that defining an eta combination variable reduces the PDE to an ODE, a nonlinear PDE like this one, where f is the dimensionless stream function and eta is the distance variable, which of course contains both y and x together. But the point is, the important observation is that it's an ODE right now, so it would be easier to solve rather as compared to the PDE that we were dealing with before. So this is what the equation is all about. Through this definition, we have come to this point, and we know what are the boundary conditions. Okay, that means on the plate, as we know that eta is defined as what is the y root over u by nu x. Okay. So with this, we know that Vx and Vy both are going to be 0, will be 0 for eta equals 0. So this is one condition that we have, and we also know that Vx is going to be equal to u when eta tends to infinity, because eta tends to infinity is essentially y tends to infinity. So this equation from this point onwards has been solved using numerical methods, and this was done by someone named Howard, and it was solved in 1950s. The complete table of eta f, the dimensionless stream function, f prime, f double prime, and the values are all listed in here. This is what the table looks like. So for different values of eta, the values of f prime and f double prime are all provided. Now, how would that help? The boundary condition is eta equals 0, f equals 0. Okay, that's straightforward. Is it straightforward? Would you say that if prime equal to 0 is straightforward? I wrote the boundary condition in here. Okay, from the dimensional or our understanding, we have written these down. Now I am writing this eta equals 0 and eta tends to infinity. I am expressing it in terms of f, not Vx or Vy. But can you say that df d eta equal to 0 at eta equals 0? Anyone help me? Just identify why df d eta is equal to 0 at eta equals 0. Anyone who can see how df data is connected with the physical parameters would be able to tell me why it is so. How can I write this expression? I'll go back to is this. Vx gives. So what is going to be the value of at eta equals 0? Please participate a little bit more than otherwise. I understand that this is not the ideal situation, but I would at least like to hear some comments from you, some comments, questions, or whatever. Can you hear me? Am I audible?
Yes, sir.
Okay. If I am audible, just try to answer that. Mm, how do I say that f prime is 0 at eta equals 0? Is it not obvious from here? At eta equals 0, that means on the solid plate, due to no slip condition, Vx will have to be equal to 0. So f prime will be 0 at eta equals 0. Would that give me some? So I have used the definition of Vx as obtained from the dimensional, non-dimensional analysis which I have performed, and I have obtained that at eta equals 0, f prime will have to be equal to 0. But does this give me an any other boundary condition that at eta equals 0, what is going to be f? What is going to be the value of f? But looking at these two, can you tell me what is going to be the value of f at eta equals 0? I understand that at eta equals 0, f prime is 0, but at eta equals 0, what is the value of f? Just concentrate on the two red boxes.
So will that also be 0?
Can you tell me your logic?
So because Vy is also 0 at eta equals 0, and
Right.
from the first box df by d eta is 0, so then we get that f is equal to 0.
Fine. So using the expression for Vy as we have obtained at eta equals 0, obviously the first term inside the bracket is 0. And for Vy to be 0, due to no slip condition, f will have to be equal to 0. Okay. So the boundary condition then is obvious that at eta equals 0, both f and f prime will be equal to 0. And again, looking at the expression, you tell me what is going to be what can you say about any other boundary condition that you can say when eta tends to infinity? What happens when eta tends to infinity? Look at these two equations and use your physical understanding. What does what can you say about f or f prime when eta tends to infinity? Physically, yeah, someone was trying to say something.
Yes, f prime becomes 1 because Vx becomes equal to u.
Right. So physically, we know that the free stream velocity and the velocity inside the boundary layer, in fact, the velocity inside the boundary layer, Vx, will approach and will essentially become equal to the free stream velocity, which is u, when we are talking about distances far from the wall. So therefore, as eta tends to infinity, this Vx by u becomes 1, and df d eta would also have a value equal to 1. So that's what I have written over here. As zeta tends to infinity, I shouldn't say equal to infinity, as zeta tends to infinity, f prime is going to be equal to 1. So the steps are unimportant, but how you convert your physical understanding of the process into these boundary conditions, that is important. And I would now like to take you to have a look at this table and see whether these numbers mean anything, whether you have whether you can use it to some extent to your advantage. These are a bunch of numbers. but can you define something? Can you extract some information out of it? So the values of eta, different values of eta are provided, f prime and f double prime. Why do they come f prime and f double prime? That's separate, but this is how the numerical solution was presented. Our job is to extract something useful from this table. So if we need to extract something useful, I need to find a set of values which has some meaning. So looking at this, can you identify the row which would be pertinent to the discussion that we were having? Eta equals 4. Does it give you something? If you go to the second column, eta equals 4. Third column, it equals 4, and fourth column. So if I consider the third column, eta equals 4, the value of the numerical value of the third column is 0.955. If I go to eta equals 5, the value of the third column is 0.991. If I go to eta equals whatever 6 or something, it becomes 0.998. So between 4, 5, and 6, do they convey some useful information that you can use? I have identified 3 rows. You have to pick the right row with some logic. It equals 4, it equals 5, and it equals 6. And concentrate only on the value in the third column. Would that give you something? If you look at the top, the what f prime is provided, and you are considering this value, this, and this.
Sir, at eta equals to 5, it is the edge of the boundary layer because here
And
Vx by u is equal to 0.99.
perfect. So at eta equals 5, if you see that Vx by u is equal to 0.99. And of course, it would be exactly 0.99, probably maybe 4.95, but that doesn't matter. In order to make it compact, simple, so we can choose this row to define what is delta. Is that clear? So at eta equals 5, the value value of f prime, that means u by u infinity, is going to be equal to 99. So this can be used to define what is delta. So what we can write is eta equals 5, and now this y, we understand this y becomes equal to delta, and u by nu x would be there. So therefore delta is going to be equal to 5x by root over rex. So that's a very compact form, very usable form, which can be equation, which can, or relation, which can be used to find out, figure out what is the value of the this boundary layer thickness at any given point. And this rex, of course, you know that it contains not only the actual location, it also contains what is the velocity. Okay, what is the velocity, that small, the capital U that you see, what is the velocity, approach velocity, and it also contains the physical properties expressed by mu by rho, or the kinematic viscosity. So this relation shows you the growth of the boundary layer as a function of the approach velocity, as a function of the physical properties and the actual location. And this correctly captures the behavior of delta, is that initially it's going to rise very fast, and then as the value of Rex increases, the rate of growth progressively decreases, and for large values of x there is almost going to be a very small change in the value of the delta. But I would like to uh, explain once again, or rather bring it to your notice, is that the definition of Rex, it we so far the Reynolds number that we have come across are always, the length scale is always across the flow. Think about the pipe diameter which is used for Reynolds number. The diameter is across the flow. This is a situation in which the Reynolds number is defined based on the length scale along the flow. That is the difference. So Reynolds number is defined using a length scale along the flow, and that's why it's called the axial Reynolds number. Whereas all other Reynolds numbers that you have come across are, the length scale uses is essentially perpendicular to the flow direction. So the numerical solution gives me a very compact relation for delta. Now, if you think about getting more information out of this, one parameter of engineering importance is delta. The question is, what could be other engineering parameter that you think would be useful in this case? For flow over a flat plate or any plate, doesn't matter, the thickness of the boundary layer is an important parameter. From engineering standpoint, is there any other parameter which you would like to know? What else is important? Can I? And if you identify that, then obviously it's you have a boundary layer thickness. Because of the boundary layer thickness, you have you have a region in which the solid and the liquid interact. The role of the solid is to reduce the velocity of the liquid. That means it impedes the flow, and the resistance offered by the solid to the flowing fluid, we have a name for that. What it is called? When a fluid flows over a solid, it tries to take the solid with it, or the solid, if it is stationary, it tries to resist the motion. What kind of a force are we talking about? What is the name of the force, common name of the force that all of you, I'm sure, know?
Shear stress.
Shear stress, but it is shear stress is definitely responsible. But what is the force due to this shear at the liquid solid interface commonly known as force? Shear stress
Friction.
is the reason.
So is it friction?
Friction, something more common that we use almost, I mean, very commonly. It is friction, no doubt about it. It is friction. But what is the most common name for that? Friction is correct. Shear stress is the cause. That is also correct. The frictional resistance is correct. But if I need to give a name to this so-called opposing force, which name comes to your mind? Haven't you heard about something called drag force? So it is the drag force whose root cause is the shear, whose root cause is also the friction. Both of you are correct in that sense. But the most common name given to this kind of force, which arises due to the viscous nature of the fluid, is known as the friction force, and it is also called the friction drag. Okay, there is something else as well, which is the lift provided by the flowing fluid over an irregularly shaped object, but that we are not going to consider here, which has more relevance in aerodynamics. We will concentrate in this part of the course only on friction drag, and the friction drag can then be calculated, as you have said, is the friction is the shear stress, but the shear stress has, I have written the I have used the subscript uh, W here to denote the wall shear stress. So it is at y equal to 0. And after I substitute, after I make all these changes, you'd see that it's the f prime at eta equal to 0, which we need in order to express everything. So you can look at these steps yourself. But what I would see is that at sorry, f double prime, I think. Yes, f double prime. That's what we need. And you look at the value of f double prime when y equals 0, that means at eta equals 0. So this row provides me with delta, expression for delta, whereas this row provides me with the expression of the drag force. And if it is drag force, uh, it something else is needed. When I show it to you, it will become clear to you. So I get this the value of this from the table, which is 0.332. Since at eta equals 0, f double prime is 0.332. So you get the tau w, the wall shear stress, which is a function of the velocity, free stream velocity, and root over Rex. But is there any question up to this point? Hmm. Okay. If not, uh, we it is good to know the value of the shear stress, wall shear stress. But in engineering, we do not use tau w to express the role of the drag force or the frictional drag. Some other parameter is commonly used, and you have used that in fluid mechanics. So what is that? It's not tau w, but a quantity which is related to tau w. When a fluid flows through a pipe, you do not write tau w. You write something else.
Friction coefficient.
Friction coefficient. Okay, so the friction coefficient or shear stress coefficient is defined as tau w by half rho u square. That is the definition of friction coefficient. So when you put the expression for tau w in here, this is the expression which you get, where CF is 0.664 by Rex. Probably you have seen it somewhere. I'm not very sure whether you have seen it or not. But the friction coefficient for flow over a flat plate in laminar flow is simply this. So therefore, the friction coefficient can be calculated as a function of Reynolds number. It can be graphically represented as a function of Reynolds number, something similar to what you have seen, what you have done in Moody's diagram. So this shear stress friction, this friction factor is has this form. But once again, I would like to point out that the friction factor that you see over here is a function of x. Same way, the delta, the boundary layer thickness, is a function of x. So two quantities that you have of engineering importance are delta, which is a function of x, and CF, which is a function of x as well. Okay, so if you like to find out what is the total force exerted by a flowing fluid on a stationary plate, you need to integrate this between 0 to L and the entire length expression which I have given here and which is obvious. So the local force, local shear stress multiplied by the area, and if I talk about unit depth, so it is simply multiplied by dx and integrated from 0 to L, the entire length of the plate would give you what is the total force exerted by the flow on the solid. So since CF is a function of x, something more commonly used which is not a function of x, which is the integrated value of CF over the entire length and then divided by L in order to obtain some sort of an average CF, is more commonly known as CD or the drag coefficient. So CF is the local shear stress coefficient, which is a function of x. And if you integrate it over the flow area and divide it by the area, what you get is CD, which is the drag coefficient. Is the concept of shear stress coefficient and drag coefficient, one which is a value which is a function of x, the other which is not a function of x, and the value of the or the expression for the delta. Are these concepts clear? Do you have any conceptual question? So this shows you that that a solution of the governing equation of the PDE invoking the use of combination of variables can lead to some very useful relations by relations as is shown in this table. But it is to be noted that this is for the simplest possible such situation of flow over a flat plate. What happens if the flow is curved? What happens especially if the flow is turbulent? Then this equation would obviously be not sufficient. There would be additional terms which will denote the turbulent transport of momentum. And even for the simplest case, you have to do a lot of mathematical jugglery, identify some dimensionless variable eta, combination variable eta, with which when you evaluate each of these terms, the PDE gets transformed to an ODE. So this underscores the utility of the analysis that we have discussed so far, but also highlights the limitation, the severe restriction that we have on any such results of delta and for example CD or CF. So what is going to be the case if it's flow over a flat, not over a flat plate, but over a curved surface? How can I treat turbulent flow in this case, which is the most common industrially relevant flow situation in most of the cases? So the analytical approach gave us very good understanding for a simple situation. It tells me that delta is going to vary with root over x. It gives me an idea of how CF is going to vary with x and with other parameters. But it is a restricted form of the solution, and we must realize that this approach is untenable for complicated geometries and for complex flow which is mixed or turbulent flow, because it is very likely to happen is that the whatever the growth of the boundary layer that you see over here, when the turbulence sets in, it is going to be something like this. The rate of growth of the boundary layer suddenly shoots up when we convert from the laminar to the turbulent, and it is going to be quite disturbed. The edge of the boundary layer will change its position with time, and it is going to be an irregularly varying or oscillating boundary layer that we have here, and it is definitely not possible to use the approach which you have done before. And this is just a piece of information, is that the Reynolds number based on the in the axial position, sorry, not C, or at transition at the changeover, is usually taken as 5 into 10 to the power 5. So we understand that Reynolds number of 2100 or whatever be that value is for pipe flow. It signifies the start of the change from laminar to turbulent, and at around 4000 or whatever, it becomes completely turbulent. So even though the process is gradual, we have to demarcate the laminar and the turbulent boundary layer, and this demarcation is set at 5 into 10 to the power 5, which is obviously, this information is obtained by the averages of large number of experiments, and this is the universally accepted value of the transition of Reynolds number, where the flow changes from laminar to turbulent, and none of the equations or none of the relations that we have obtained, the growth of the boundary layer can be accurately predicted by this relation only up to this point. Beyond this point, since the governing equation is different, this relation will also not hold good. Same is true for the expression for CF. All these are for laminar flow. For turbulent flow, they will be different, and this again shows us that we need to have something of a more robust technique to handle boundary layers than the analytical approach that we are discussing so far. Any question? Okay, so I will take a break, and once I come back, we will solve some problems based on whatever we have discussed so far. Uh, you can see the slide and hear me.
Yes, sir.
Okay. This part of the class will be some sort of a tutorial. Uh, the first problem that we are going to discuss is these are the numerical results. I have already discussed with you, and you need to find out what is delta star by delta, and delta star is the displacement thickness. The evaluate the value of this ratio, the numerical value of this ratio for eta equals 5 and as eta tends to infinity. And also, that's the first part. And the second part is Vy, the ratio of Vy by U at the edge of the boundary layer. So you have to use this table, uh, use the definition of delta star that I have discussed. So do that, and then we'll discuss. Give it a try, and then I will discuss. The first part, A. And the definition of delta star, I'll reproduce for your head. So that's the definition of delta star. And of course, you have to use uh, the definition of eta, where eta is simply y root over u by nu x, where nu is the kinematic viscosity, x is the actual distance. Whenever you have questions or if you have completed this, please let me know. You realize that in order to use the table, you need to change this y into eta, which is straightforward. So, and not only you have to change y to eta, but you will also have to change this u by u infinity into something the values of which are provided in the table. So in the definition of delta star, in order to evaluate delta star by delta, whatever you have on the right hand side, u by u infinity and dy will have to be changed into parameters, the values of which are provided in the numerical in the table that's to the left. So essentially, I need an expression for delta star in terms of the parameters shown in the table. Anyone with something to discuss or whatever progress that you have made, if you can, one of you can tell me, and then I will start the discussion. It's a very straightforward problem. Could anyone get this expression, delta star expression, converted into eta and other and else? So let me start with this then. As I mentioned, eta is related to y and x in this form. So what you get then is I need to change this dy and this u by u infinity into quantities which are shown in the table. So of course dy is simply then going to be equal to d eta root over mu x by u. And delta star in the formula that we have is going to be 0 to eta and 1 minus Vx by u, and d eta can now be this is what we should get. And then ultimately, what we get delta star is, if I take this out, what should be there inside the first bracket? What should I write inside the first bracket in place of 1 minus Vx by u?
1 minus theta.
1 minus
df by dt.
df by deta. So now you can see that we are in a position where I have changed the uh, I have started with the definition of delta star and converted it into d-eta, etc. The thing that is still remaining is this. So what you can in your, if you look at the question here, you're going to find out delta star by delta in terms of for some value of eta. So I am pretty much confident that I will be able to handle the integrand, but I am missing delta over here. So do you feel that this is something which we can uh, convert to delta?
Yes, sir. That should be equal to delta.
Delta or something else? Just think, and you are in the right track.
So because this is equal to y by eta, and eta is y by delta x. So
Sir,
maybe in
sir, how did we bring that root Vx by u outside the integral? Because it is dependent on eta, if I'm not wrong.
Sir,
What
it
was
can
the
sir, it can be converted to delta by just phi x by root rdx is equal to delta, that
uh,
expression.
can you repeat what you have said just a few minutes? Just the last person who has said something.
Yes, sir.
Sir,
Sir,
I can
I was asking that how did we bring root
no
ux
no
by
the this statement after that, the last student who spoke something about nu x by u.
sir, I was saying that delta is equal to phi x by root over axial Reynolds number. So root over axial Reynolds number is in the terms, I mean, that is their root over. So
Yes.
therefore we can convert it
So what
as a
is what
delta. Yes, sir.
okay? To continue with what the statement that you have made, let me go back a bit. You are talking about this one, right?
Yes, sir.
Okay. So if that's the case, then your delta by 5 is x by root over rex. So, or rather, you are talking about this part. Maybe this the square. I mean, the rectangular bracket is something more meaningful in here, where we can see that 5 equals delta root over u by nu x. So keep this in mind, and let's go back to the problem that we are talking about. So what are you going to say about nu x by u? I'll go back to that once again. What is nu x by u in this case? Isn't it delta by 5? This which we have obtained in our derivation just a few, I mean, maybe 10-15 minutes back. If I concentrate this, I would be able to convert this delta star as delta by 5, and then whatever we have on the right hand side. Do you agree or not? Or I mean, do you agree? Root over nu x by u is simply delta by 5. I will go back to this once again. If you look at the expression over here, if you simplify this, if you substitute the value of expression for rex, you are essentially it's the same one. So from here delta by 5 is simply the inverse of this, and that's what we have in this expression, root over nu x by u. So this must be equal to delta by 5. So if I go back to the if I write it, then what I get is delta star is equal to delta by 5, and the integrand then becomes 0 to some value of eta 1 minus f prime times d eta. And if I integrate this, if I do this integration equal to 1 by 5 eta minus f from 0 to eta. And here I have to use the value of eta equals 5 in one case and eta equals infinity, and find out what is the ratio delta star by delta. Is this clear?
Sir, I had a conceptual question. Sir, I could not understand how we substituted Vx in place of small u.
Uh, one more time your question, please.
Sir, I could not understand how we substituted Vx in place of small u.
Oh, okay. It doesn't matter. I mean, Vx and U, I mixed up the notations. Vx and U are the same. Small u are the same. It's the capital U, which is the free stream velocity, and the axial velocity sometimes it's represented by Vx, or the axial component of velocity sometimes it's expressed by u. So it is u and small v in some case, and vx and vy in some other case. So they are the same.
Okay, sir. Thank you, sir.
Okay. The problem that you are going to have is so let's go back to this the table and try to see what is this going to be. So I'll go back to this table, and what you have seen is that delta star by delta equals 1/5 of something. Uh, 1/5 of what was the result? 1/5 of eta minus f. So 1/5 of eta minus f. So you know the value of eta is 5, and the corresponding value of f is 3.28 something. So you are evaluating delta star by delta to be equal to 1/5 of eta minus f from 0 to eta. So as far as this part is concerned, you do not have a problem, because the value of eta at 5 and the value of eta at value of sorry f at 5, these are known to you. You substitute 5 minus 3.28 and you get the value of delta star by delta for this value of eta. But how are you going to find out eta equals infinity? It's only up to 8.4 that's provided. Purposefully nothing is given nothing is given beyond 8.4 in the Haworth numerical solution. Think and answer.
So because anything beyond eta equals 5 can be considered infinity, because the free stream velocity won't change.
I agree with you, but do you mean to say that if I say 5 here, the corresponding value of f is going to be 3.28? But let's see if I take 7 and this becomes 5.27. So I accept your observation that anything beyond eta equals 5, it's not changing much. But can you be more specific? Just look at the numbers and try to see.
So specifically, it could be eta equals 8, beyond 8 because f dash is equal to 1.
Okay, but wouldn't it be rather, I would say, more obvious if I say at value of eta equals 8, 8 minus 6.27, whatever 923, and for eta equals 8.4, 8.4 minus 6.67. It's not the value of eta or not the value of f. The difference becomes invariant for a value of eta greater than 8. So I can substitute eta equals infinity by eta equals 8. The difference will remain unchanged from this point onwards. Agreed? So the difference doesn't change for value of eta corresponding to 8. 8 minus 6.27 and 8.4 minus 6.67 are essentially the same, but the difference, as you have previously pointed out, 5 minus 3.28, I mean, there is still some changes in over here, but this is a value where it doesn't change. But if you say that okay, I could say the same thing for eta equals 7 and eta equals 7.4. I also agree with that because there is a change of point point 0.4, but there is some change in the fifth place of decimal, fourth or fifth place of decimal. In this case, they are totally completely identical. So if you give the logic correct and say that I am going to take a value of eta equals 7, your value will not change much. I will accept that. But if you want to be exact, it is the value of eta equals 8 that we should pay. But if someone gives the correct logic and say that eta equals 6, this difference is also approximately invariant. I would accept that. Okay, now you concentrate on the second part. Before you concentrate on the second part, I would like to ask you something about the boundary layer. I'll go back to the first figure of what we see over here. The boundary condition for y equals 0 is that Vx and Vy are both equal to 0 at y equals 0. That's a no slip condition. When we reach the so-called edge of the boundary layer, we say that Vx is going to be equal to u infinity. But we were silent about Vy. What is your impression? What is your idea about the value of Vy at the edge of the boundary layer, where Vx is equal to u infinity? What do you think? That may have happened. Is it equal to 0? Or can it be equal to 0? This has important implications in some industrial applications as well. But I would like to know your opinion about the possibility, or what are the possibilities of Vy? Is it equal to 0?
So it can be 0 because the free stream velocity does not have any y component.
Okay. Um, uh, any what's your name? I couldn't see. I cannot see right now who you are.
Sir, I'm Adrija.
Adrija. Okay. So anyone who has a different opinion about what Adrija has said? What she said is that since the free stream velocity doesn't have any y component, So I mean Vy for that for the portion at the near the top is 0. So obviously Vy at this point will also be equal to 0. Is there any anomaly in her statement? Well, Adrija, you can answer as well. Do you feel that there is a problem with the statement that you have made?
So there might be, I'm not sure, because it suddenly, how does it suddenly become zero? That may be a question.
Let's take it the other way around. Let's assume that it is 0. What you said is correct, that it is equal to 0 at y equals whatever delta. What happens to any point to the right of it? Any point, let's say at this point, I say that Vy is 0. So what do you feel is different between this point and this point as far as the boundary layer is concerned? Are the flow rates the same at this flow rates through the boundary layer? At this point, point 1, and at this point, point 2. Are the flow rates the same or different? Because the Vx is a very weak function of x. So Vx doesn't change much with x. Vx changes with y. So whatever flow area that was available at location 1, and you can see the cursor, right? The
Yes, sir.
cursor, okay. So whatever flow rate that you had over here at 1 and whatever flow rate that you had over 2, obviously the flow rate at 1 is going to be less than the flow rate at 2. So how would this new mass come in if we do not have a Vy? If we do not have a non-zero Vy? So if I draw, if I think about the flow rate through, sorry, if I think about the flow rate through this and the flow rate through this, obviously the flow rate through the second location, second plane is going to be more than that of 1, and this can only happen if we have some non-zero Vy in here. So the question can also be put in a different way. Do you think the edge of the boundary layer is a streamline? What would be your answer to that? The black line which I have drawn over here, whether the edge of the boundary layer is a streamline based on our discussion so far. What are the properties of a streamline? Two streamlines cannot cross. Anything that starts on a streamline stays on the streamline. And there's one more property which will let you decide on the question whether the edge of the boundary layer is a streamline or not. Any other property that comes to your mind? The property of the streamline, another property of streamline is no two streamlines can cross. Nothing can cross a streamline. Do you think you would be able to call the edge of the boundary layer a streamline now?
No, sir, if we have a non-zero y,
We
then
have non-zero y, and we have to have a non-zero Vy because otherwise the layer would not grow. So the two ways by which this question can be posed is find out what is Vy, which you are going to do. And the second thing is the age of we understand that the age of the boundary layer is not a streamline. So that's the second important thing which we would even we would we can infer. So the values of the answer for the first part of The answer for the first part, delta star by delta, would be equal to 0.34334 for for eta equals 5 and equal to 0.34415 as eta tends to infinity. And then we'll go for the evaluation of the Vy by u. So if we try to find out what is Vy by u at the edge of the boundary layer. And we write the expression for Vy, which I have shown before. And of course, you do not have to remember any of these, that you know that I will always provide you with the expressions. So from here, you can write Vy by u, and you would get this to be equal to 1 by 2. This you should check on your own. Reynolds number based on x, eta f prime minus f. This is the expression for this is the expression for Vy by u that you would get, and for at the edge of the boundary layer, you can write eta equals 5, and the corresponding value of f you could get from the table to be equal to 3.28, whatever something, and therefore the final expression for the velocity at the edge of the boundary layer, you would see that this is 0.84 by root over Rex. So this is the expression for the non-zero velocity at the edge of the boundary layer. And it also shows what we would expect is that as the Reynolds number increases, as we go more and more into the actual into the actual position, the value of Vy decreases, and therefore the rate of growth of the boundary layer decreases with increase in x. Okay, so initially it will grow faster since the value of Reynolds number is small, but as Reynolds number increases, the value of Vy increases, value of Vy decreases, and the growth of the boundary layer is somehow going to be arrested. The important point still remains is that the edge of the boundary layer is not a streamline. In the remaining 6-7 minutes, I will discuss the last problem, and I will only give you the pointers, and you are going to solve it on your own. So you have a laboratory wind tunnel, okay, that has a section which
So
is.
I have a doubt in the previous example.
Okay, please tell
So
me.
you're saying that the flow rate increases as x increases. So can you explain that part?
Mm, I would say that the amount of mass which is this is the boundary layer. So if you take a cross section and find out the amount of mass crossing this and the amount of mass crossing this has to be more than this. Otherwise, the boundary layer would not grow. I mean, if this is more than this, which obviously it is, then there has to be some sort of inflow through the edge of the boundary layer. Otherwise, how can it grow? So this essentially means that very close to the edge of the boundary layer, my Vy at y equals delta cannot be 0. If I move very far away from it, Or if I go to a point where the x is very, very large, then this becomes the x-axis parallel to the plate. So there is almost no growth. And Vy therefore is going to be a decreasing function of Reynolds number, which you see over here. But in order to maintain the continuity, since the area increases drastically, at least in the initial part of the boundary layer growth, there has to be some flow from the bulk through the edge of the boundary layer into this string. So this has to happen. Otherwise, physically, you cannot have a situation in which you have more area. And as I have mentioned, if I take a 1 second, let me. Where is it? What did I do? Forget about it. If I take this plane and this plane, we understand that Vx is a weak function of x. Okay, Vx varies drastically with y, but doesn't vary much with x. So the Vx between this point and this point would probably be very close to each other. Vx at this point and this point are close to each other, but you have additional area available to you now. So who's going to, how this additional Vx is to be accounted for? The flow through this region is going to be accounted for unless we have some flow into the system with a non-zero Vy. Am I clear now?
Yes, sir.
Okay. All right. So what we have in this problem is a wind tunnel, which is a square 305 by 305, whatever, millimeter or something. So it's all the way like this. And there is a station 1 and a station 2, which are provided. Now, boundary layer profiles are measured at two cross sections and displacement thicknesses are evaluated. So we know what displacement thicknesses are. At section 1, where the free stream speed is U1 equal to 26 meter per second and displacement thickness is 1.5 meter. At section 2, delta 2 star is 2.1 millimeter. So over here, delta 2 star is 2.1 millimeter, and over here delta 1 star is equal to 1.5 millimeter. And the free stream velocity at this point, which is u1, is 26 meter per second. Uh, you need to find out the change in pressure, static pressure between 1 and 2. There is one concept, just one concept you have to identify, and then the problem is extremely simple. Can you identify the concept that is involved in this specific problem? What can you say between 1 and 2? What type of a flow is this when you consider displacement thickness? I once again go back to the concept of displacement thickness. If the displacement thickness is a concept where the entire flow is treated as inviscid when you move this plate up by a distance delta star. So if I move this plate up by delta star, then essentially the rest of the flow becomes inviscid. That was the concept of displacement thickness. Now let's come back to our problem over here. How do I convert this problem that is posed over here to a problem of inviscid flow? if I reduce the cross section available by certain distance, then through that reduced area, the flow can be treated as inviscid. Am I clear and correct? If I could reduce from all sides by some distance, then the end in then and the result of which is this flow through that reduced area is inviscid, then what is the distance by which I have to reduce it for my calculation?
2.1 mm.
2.1 mm at location 2 and 1.5 mm at location 1. So the entire problem then becomes an inviscid flow where I have flow through this and obviously over here. So station 1 will have area. What will be the area at station 1 for inviscid flow? Instead of 305 into 305, what would be this area? I have reduced it. So what would be this area? Area at 1. It is inviscid flow now. So it must be equal to 2 into 1.5 millimeter. And over here, it's going to be 2 into 1.5 millimeter in order to account for growth of boundary layer from all 4 sides. Am I clear? You have any question? The whole idea of displacement thickness is to transform the flow from a viscous flow to an inviscid flow. So if I constrict the area by this much both, from both sides, then what I have is a new area through which the flow can be treated as inviscid, and at location 2 it is simply going to be 305 minus 2 into whatever it is, 2.1, and 305 minus 2 into 2.1, this much of millimeter square. So at 1 and 2 the flow is inviscid now. The problem states that I have to calculate the change in pressure. So if the flow is inviscid, what can I use in order to find the pressure difference between the two? Which equation should I use? Bernoulli's equation. So it becomes a straightforward problem of Bernoulli's equation, and I will assume that there is no effect of gravity, plus V1 square by 2 plus GZ1, obviously, which is 0, would be P2 by rho plus V2 square by 2 plus GZ2, and this would be also equal to 0. So you can write P1 minus P2 is half of rho U1 square times U2 by U1 whole square minus 1. That's going to be your expression, and the expression, the final expression would be P1 minus P2 by half rho U1 square is equal to U2 by U1 square minus 1. And we know from equation of continuity A1 by A2 equal to U2 by U1. And this is L minus 2 delta and L minus 2 delta star, obviously star whole square 1 and 2. And then you could find out what is the numerical value of this. And this is going to be about 0.016. So less than a 2% change. Okay, and the only other factor which you have to keep in mind, just one more minute, is the result as a fraction of free stream dynamic pressure. And the free stream dynamic pressure is obviously this, where the kinetic energy has been completely converted to pressure, which is also which is known as the static pressure, or you can convert it into static pressure that you can measure in using a pitot tube. This is also known as the dynamic pressure. Any question on this? So that's all for today. And next class, we will start with the momentum integral equation, possibly, unless you have any other question, or just send an email to me if you have further questions, and I will discuss that in the next class.